Our senses paint a picture of reality. Objects seem solid. Their movements appear predictable. We live in a world where the laws of physics seem straightforward, where cause and effect are clear, and where the tangible nature of objects is something we rarely question. But this familiar world dissolves at the subatomic level, revealing the bizarre and beautiful realm of quantum mechanics. Here, the rules that govern our everyday experiences no longer apply. Instead, we find a universe that operates on principles that are both mystifying and awe-inspiring. Here, particles exist in a haze of probability, defying our everyday intuition. They don't have definite positions or velocities until we observe them. This phenomenon, known as superposition, means that particles can be in multiple states at once, a concept that challenges our very understanding of existence. Welcome to a universe where the very fabric of reality is woven from the threads of uncertainty and paradox. In this quantum realm, the act of observation itself can alter the state of what is being observed, a principle famously illustrated by Schrödinger's cat thought experiment. Imagine a world where an object can be in two places at once. This is not just a theoretical curiosity, but a fundamental aspect of quantum mechanics. Superposition allows particles to exist in multiple states simultaneously, leading to phenomena that seem impossible by classical standards. Picture a realm where particles communicate instantaneously across vast distances. This phenomenon, known as quantum entanglement, suggests that particles can be interconnected in such a way that the state of one instantly influences the state of another, regardless of the distance separating them. This is the strange and counterintuitive landscape of quantum mechanics. It is a world that defies our classical notions of space and time, where particles can tunnel through barriers and where the future can influence the past. It is a realm that challenges our classical understanding of the universe, forcing us to confront the limits of our perception and embrace a new, more profound vision of reality. Quantum mechanics compels us to rethink the very nature of existence and the fundamental principles that govern the cosmos. The journey into quantum mechanics is a descent into the heart of matter, a quest to unravel the fundamental building blocks of the cosmos. It is an exploration that takes us beyond the visible and into the realm of the infinitesimally small, where the rules of the game are entirely different. It is a journey that will lead us to question the nature of reality itself and to marvel at the elegance and strangeness of the quantum world. As we delve deeper, we uncover a universe that is far more intricate and interconnected than we ever imagined. A universe where the boundaries between reality and possibility blur, inviting us to explore the mysteries that lie at the very core of existence. The quantum revolution began quietly, with a whisper of energy. It was a subtle yet profound shift that would eventually ripple through the very fabric of scientific understanding, altering the course of physics forever. In 1900, Max Planck, a German physicist, stumbled upon a curious phenomenon while studying the radiation emitted by heated objects. His meticulous experiments and keen observations led him to a startling conclusion that defied the conventional wisdom of the time. He discovered that energy, long thought to be continuous, was actually emitted in discrete packets, or quanta. This was a radical departure from the classical theories that had dominated physics for centuries, suggesting that at a fundamental level, nature operated in a series of tiny, indivisible steps. This groundbreaking discovery, for which Planck was awarded the Nobel Prize in 1918, marked the birth of quantum mechanics and forever changed our understanding of the universe. The implications of his work were vast, opening up new realms of scientific inquiry and technological innovation. Planck's constant, denoted by the letter h, is a fundamental constant in physics that relates the energy of a photon to its frequency. This simple yet profound relationship forms the cornerstone of quantum theory, linking the macroscopic world we experience with the mysterious and often counterintuitive behavior of subatomic particles. It is an incredibly small number, approximately 6.626 times 10 to the negative 34 joule-seconds, yet its implications are profound. This tiny constant governs the interactions of particles at the smallest scales, dictating the rules of a realm where the classical laws of physics no longer apply. Planck's constant governs the behavior of particles at the subatomic level, dictating the rules of a realm where energy is quantized and the classical laws of physics break down. In this quantum realm, particles can exist in multiple states simultaneously, and their properties are defined by probabilities rather than certainties. The discovery of Planck's constant was a seismic event in the history of physics. It not only challenged the established paradigms, but also laid the groundwork for future discoveries that would further unravel the mysteries of the quantum world. It shattered the prevailing classical view of a continuous and deterministic universe, paving the way for the development of quantum mechanics and its revolutionary implications for our understanding of the cosmos. The quantum revolution has since led to numerous technological advancements, from semiconductors and lasers to quantum computing and cryptography, each building on the foundational principles that Planck's work helped to establish. Today, the principles of quantum mechanics continue to drive innovation and discovery. Quantum computing promises to revolutionize fields ranging from cryptography to materials science, while quantum cryptography offers unprecedented security for digital communications. These advancements are a testament to the enduring impact of Planck's pioneering work. The influence of quantum mechanics extends beyond the laboratory and into our everyday lives. Technologies that rely on quantum principles, such as MRI machines and GPS systems, have become integral to modern society. As we continue to explore the quantum realm, we uncover new possibilities that challenge our understanding and expand the horizons of human knowledge. The future of quantum research holds endless possibilities. As scientists delve deeper into the quantum world, they uncover phenomena that not only challenge our current understanding, but also inspire new theories and technologies. The spark of revolution ignited by Planck over a century ago continues to burn brightly, guiding us toward a future where the boundaries of what is possible are constantly being redefined. One of the most mind-bending concepts in quantum mechanics is wave-particle duality. This principle states that particles, like electrons and photons, can exhibit both wave-like and particle-like behavior. Imagine a beam of light. Sometimes it acts like a wave, diffracting through narrow slits and interfering with itself. Other times, it behaves like a stream of particles, carrying discrete amounts of energy. This duality is not limited to light. Electrons, the fundamental particles that make up atoms, also exhibit wave-particle duality. In experiments, electrons have been shown to diffract through crystals, just like waves. Yet they also interact with other particles as discrete entities, carrying a specific charge and mass. This inherent ambiguity at the heart of quantum mechanics is unsettling to our classical intuition, which seeks to categorize objects as either waves or particles. Yet it is a fundamental aspect of the quantum world, a testament to the limitations of our everyday experience in describing the subatomic realm. Section 4. Heisenberg's uncertainty principle, embracing the unknown. In the quantum world, certainty gives way to probability. Heisenberg's uncertainty principle, formulated by German physicist Werner Heisenberg in 1927, states that we can never know both the position and momentum of a particle with perfect accuracy. The more precisely we measure one quantity, the less we know about the other. Imagine trying to pinpoint the location of a fast-moving electron. The act of observing it, perhaps by bouncing a photon off it, inevitably disturbs its momentum. The more accurately we try to determine its position, the more we alter its momentum, and vice versa. This is not a limitation of our instruments, but a fundamental principle of nature. Heisenberg's uncertainty principle highlights the probabilistic nature of the quantum world. It tells us that at the subatomic level we can only predict the likelihood of finding a particle in a particular state or location. The universe at its core is a dance of probabilities, not a clockwork mechanism. Section 5. Quantum tunneling, through walls of impossibility. Imagine a ball rolling up a hill. You can picture it, right? The ball needs a certain amount of energy to reach the top of the hill. Classically, if the ball doesn't have enough energy to reach the top, it will roll back down. This is what we observe in our everyday world. But in the quantum world, things get a lot more interesting. There's a chance the ball could tunnel through the hill, appearing on the other side as if by magic. This isn't just a trick or an illusion, it's a real phenomenon. This is quantum tunneling, a phenomenon where particles can pass through energy barriers that would be insurmountable according to classical physics. Imagine a particle facing a barrier it shouldn't be able to cross, yet somehow it does. Quantum tunneling is a consequence of the wave-like nature of particles. In the quantum realm, particles aren't just tiny dots, they also behave like waves. Just as a wave can extend beyond a barrier, so too can the wave function of a particle. This wave function represents the probabilities of where the particle might be found. This means there's a non-zero probability of finding the particle on the other side of the barrier, even if it doesn't have enough energy to overcome it classically. It's like having a small but real chance of winning a lottery. Quantum tunneling plays a crucial role in many natural phenomena, from nuclear fusion in stars to the operation of transistors in our electronic devices. Without it, the sun wouldn't shine, and our modern technology wouldn't function. It is a testament to the strangeness and wonder of the quantum world, where the seemingly impossible becomes possible. The rules are different here, and they challenge our understanding of reality. Quantum tunneling isn't just a theoretical concept, it has practical applications too. For instance, in medical imaging techniques like MRI, quantum tunneling helps us see inside the human body with incredible detail. In chemistry, quantum tunneling allows certain reactions to occur at lower temperatures than would otherwise be possible. This has profound implications for understanding how life processes work at the molecular level. In the field of superconductors, quantum tunneling is essential for the phenomenon of superconductivity, where materials conduct electricity without resistance. This could revolutionize energy transmission in the future. And let's not forget quantum computing. Quantum tunneling is a key principle that allows quantum computers to perform complex calculations at speeds unimaginable with classical computers. The quantum world is full of surprises, and quantum tunneling is one of its most fascinating features. It reminds us that the universe is far more mysterious and wondrous than we can ever fully comprehend.